What is the largest single thing in the universe? The answer is not a star or a galaxy. It is a cosmic puzzle that will take us on a journey across scales so immense they defy comprehension. By the end of this journey, you will know the true contenders for the title of biggest thing in existence and understand the very architecture of the cosmos. We will explore invisible structures that bind galaxies together and confront a wall so vast it challenges the fundamental laws of the universe. Are you ready to discover what truly holds the universe together? But before we can name a champion, we have to agree on the rules of the contest. What does biggest actually mean? On Earth, it seems simple. An elephant is bigger than a mouse, but in the cosmos, the definition gets fuzzy fast. Is the biggest thing the one with the most mass, the sheer amount of stuff it contains? Or is it the one with the greatest physical width, the distance from one side to the other? Or perhaps it is the object with the most volume, the total space it occupies? These are not the same thing. Imagine a mountain of lead and a cloud of cotton candy the size of a city. The mountain is incredibly heavy, packed with mass, while the cloud is overwhelmingly wide but almost weightless. Which one is truly bigger? The universe presents us with similar puzzles. A star can be so dense that a single teaspoon of its material would weigh more than a car, yet it occupies a relatively small space. Meanwhile, a vast, wispy nebula can stretch for light years but contain less total material than a single star. This is the first challenge in our search. We are not just looking for one champion, but several, each crowned in a different category. And this leads us to structures so immense they make galaxies look like specks of dust. We are about to venture into the realm of superclusters and the cosmic web, where the very idea of a single object begins to unravel. Our own cosmic backyard provides a perfect starting point for this journey of scale. The solar system feels immense, a place where distances are so great we measure them with the speed of light. Light itself takes about 8 minutes to travel from the Sun to Earth. But that is just the beginning. To reach the outer planet Neptune, that same beam of light travels for over 4 hours. If you could line up every planet end to end, the entire parade would fit comfortably within the average distance between the Earth and the Sun. This is the first humbling realization. Despite all those majestic worlds, our solar system is overwhelmingly, almost incomprehensibly, empty. The Sun contains 99.8% of all the mass in this entire system, a true titan of gravity and light. Yet the physical territory it rules extends far, far beyond the last planet. A vast spherical shell of icy debris known as the Oort cloud is believed to encase everything, the final frontier of the Sun's gravitational influence. From one end of this cloud to the other is a distance of roughly 2 light years. That means it takes light an entire year just to travel from the cloud's inner edge to its outer boundary, and then another full year to complete the journey. This is the true size of our home system, a realm defined not by its objects, but by the mind-numbing voids between them. And yet, as we prepare to step outside its borders, we must understand that this entire colossal structure, from the fiery Sun to the deepest frozen Oort, is about to shrink into a mere speck. Even our entire solar system, with its Oort cloud spanning 2 light years, is just a single point of light when we pull back the view. We are leaving our home behind and entering the grand city of stars we call the Milky Way galaxy. Picture a colossal whirlpool of light, a spinning disk so vast that it defies every earthly sense of scale. This is our galactic home, a spiral galaxy containing an estimated 100 to 400 billion stars. Our Sun is just one among this unimaginable multitude. The sheer physical size of this structure is the true shock. From one edge of its glowing disk to the other is a distance of about 100,000 light years. This means a beam of light, the fastest thing in the universe, would need 100,000 years just to make a one-way trip across it. If you could shrink the Milky Way down to the size of North America, our entire solar system, from the Sun to the Oort cloud, would be smaller than a single grain of sand. We reside in one of the galaxy's spiral arms, a stellar suburb far from the brilliant, crowded core. Our position here is not special, just a quiet neighborhood in an immense metropolis of stars, gas, and invisible dark matter that holds the entire city together with its gravitational glue. This galaxy feels like the entire universe, but it is merely our local island in a much vaster cosmic ocean. But the Milky Way is not a lonely island. It is the heart of a bustling galactic community, a cluster of over 50 galaxies all bound together by their mutual gravity. This is our local group, a family of islands in the cosmic ocean. Within this family, two giants dominate the scene, our own Milky Way and its great rival, the Andromeda Galaxy. Andromeda is a titan in its own right, even larger than our galaxy, a magnificent spiral that you can sometimes see with your naked eye on a clear, dark night as a faint, fuzzy smudge. These two giants are not static neighbors. They are locked in a slow, cosmic dance, falling toward each other across the immense void. Billions of years from now, the Milky Way and Andromeda are destined to collide and merge, their stars weaving together to form a new, colossal galaxy. Yet, even in this dramatic future, the scale of their interaction is almost peaceful, with vast distances between stars making actual stellar impacts incredibly rare. The entire local group, with all its dozens of smaller satellite galaxies swirling around the two giants, occupies a region of space more than 10 million light-years across. To cross this local neighborhood, light needs 10 million years. This single fact shrinks our grand Milky Way from a sprawling metropolis into a single district in a much greater metropolitan area, a mere borough in an immense supercity of galaxies. Even our entire local group, a 10 million light-year wide collection of galaxies, is just a small province within a continent of staggering proportions. This is the Virgo Supercluster, a vast archipelago of galaxy groups all bound together by the same invisible threads of gravity. We are no longer looking at a city of stars or a metropolitan area of galaxies, but an entire supercontinent in the cosmos. The Virgo Supercluster contains over 100 distinct galaxy groups just like our own local group, each one a swirling family of dozens or even hundreds of galaxies. All of these groups, including ours, are slowly flowing in the same direction, pulled by a common and immense gravitational tide. This entire cosmic continent is on the move, drifting toward a mysterious and powerful focal point known as the Great Attractor, a gravitational anomaly so potent it pulls on millions of galaxies from its hidden location. The scale of this structure is almost impossible to internalize. From one remote edge of the Virgo Supercluster to the other spans approximately 110 million light-years. To cross this single supercluster, a beam of light would need to travel for 110 million years, a journey that began when dinosaurs still roamed the Earth. Every star and every galaxy you have ever seen in the night sky resides within this single, unimaginably large structure, a mere neighborhood in an even grander universe. The Virgo Supercluster, for all its staggering size, was just a piece of a much grander design. In 2014, astronomers made a discovery that completely redrew our cosmic map, revealing our true home in the universe. They gave it a name from the Hawaiian language, Laniakea, meaning immense heaven. This is our cosmic continent, a structure so vast it makes the Virgo Supercluster seem like a single mountain range. So how do you even map something of this scale? You do not just take a picture. Instead, you listen to the universe's motion. By meticulously tracking the subtle drift of thousands of galaxies, scientists could trace the rivers of gravity flowing through intergalactic space. Every galaxy in our local universe is on the move, pulled by the combined gravitational tug of all the matter around it. Mapping this flow is like watching leaves caught in a gentle current, revealing the shape of the entire stream. The boundaries of Laniakea were defined by the watersheds of these cosmic currents, where the flow of galaxies diverged, heading toward different gravitational basins. They marked the continental divide. This revealed Laniakea as a spectacular filamentary network, a web of galaxy clusters connected by tendrils of light, all flowing toward a single, immense gravitational center known as the Great Attractor. This is our definitive cosmic address. Our local group, the Milky Way, our solar system, and everyone on Earth, all reside within this single, flowing structure that spans an almost unbelievable 500 million light-years. To cross Laniakea, light would need to travel for 500 million years, a journey that began long before complex life existed on our planet. We are not just living in a galaxy or even a supercluster. We are inhabitants of a specific, flowing continent in the cosmos, a single thread in a tapestry of unimaginable size. And yet, this immense heaven is itself just one island in an even larger sea. Laniakea is a continent of galaxies, but it is not the only one. Beyond its flowing borders, the universe reveals structures of such immense scale that they challenge our very definition of an object. We are entering the realm of the cosmic walls, the largest known arrangements of matter in existence. These are not solid barriers, but colossal filaments and sheets of galaxies, the dense threads of the cosmic web. One of the most famous is the Sloan Great Wall, a discovery that stunned astronomers with its sheer proportions. Picture a single, staggering chain of interconnected galaxy clusters and superclusters, a river of light and gravity stretching for over 1.3 billion light-years across the cosmos. To grasp that distance, consider a beam of light, the universe's ultimate speedster. If it set off from one end of the Sloan Great Wall, it would travel for 1,300 million years before reaching the other side. That entire journey would take longer than the Earth has existed as a planet. This single structure is so vast that it should not exist according to some of our early models of the universe, which predicted a more uniform distribution of matter on the largest scales. It is a cosmic behemoth that forces us to reconsider the fundamental architecture of everything. Yet, even this wall is just one thread in the grand tapestry. The search for the biggest thing is about to confront a discovery that seems to break the rules of physics itself. Yet even these billion light-year walls are dwarfed by a discovery so immense it seems to defy the laws of physics. The current champion, the single largest known structure in the entire observable universe, is the Hercules-Corona Borealis Great Wall. Its discovery was not made by photographing a vast shape in the sky, for such a structure is far too large and faint to see directly. Instead, astronomers had to become cosmic detectives, piecing together its existence from fleeting, violent clues known as gamma-ray bursts. These are the most powerful explosions in the cosmos, the final death cries of massive stars. By mapping the locations of thousands of these bursts, scientists noticed an impossible concentration, a startlingly dense patch of stellar cataclysms spread across an area of the sky covering the constellations of Hercules and Corona Borealis. This was not a random scattering, it was the ghostly outline of a structure, a cosmic skeleton traced in fire. The true scale of this skeleton is almost beyond comprehension. The Hercules-Corona Borealis Great Wall spans an estimated 10 billion light-years from one end to the other. Hold that number in your mind, 10 billion light-years. The entire observable universe is only about 93 billion light-years across. This means a single structure, a single connected arrangement of galaxies and dark matter, takes up more than 1/10 of the entire visible cosmos. A beam of light which could cross our Milky Way in 100,000 years would need 10 billion years to travel from one end of this wall to the other. That is more than half the current age of the universe itself. This discovery created a firestorm of controversy, for it appears to challenge one of the most fundamental assumptions in all of cosmology, the cosmological principle. This principle states that on the very largest scales, the universe should look roughly the same everywhere, a uniform and homogeneous cosmos. There should not be structures so gigantic that they create a lopsided universe. The Hercules-Corona Borealis Great Wall is so colossally large that it seems to break this rule, posing a profound question that cosmologists are still struggling to answer. Is this wall a statistical fluke, a rare overdensity in an otherwise uniform expanse, or is it a sign that our understanding of the universe's very foundation is fundamentally incomplete? So how can a wall 10 billion light-years across even exist? The answer lies in the hidden architecture of the cosmos, the framework upon which all these colossal structures are built. This is the cosmic web, the fundamental blueprint of our universe. Forget the idea of galaxies scattered randomly through the void like lonely islands. Instead, picture the universe as a single, interconnected organism with galaxies strung along vast, thread-like structures of invisible dark matter. These are the cosmic filaments. They are the universe's superhighways, immense rivers of gravity that flow through the emptiness, connecting galaxy clusters and superclusters in a delicate, shimmering network. Between these brilliant threads lie the cosmic voids, unimaginably vast and almost completely empty deserts of space where few galaxies dare to form. What we perceive as a great wall is simply a dense knot, a tangled intersection within this greater web. It is the place where multiple cosmic filaments converge, piling up galaxies and dark matter into a staggering concentration. Stunning supercomputer simulations reveal this structure not as a solid object, but as a dynamic, flowing system. It looks like a colossal neural network, a cosmic brain of unimaginable scale, with filaments acting as the nerve fibers and galaxy clusters firing like brilliant nodes. This cosmic web is the true skeleton of the universe, the scaffolding that has guided the growth of everything we see since the dawn of time. And the material that forms its strongest threads is not the familiar stars and gas, but something we cannot see at all. This cosmic web is defined as much by its emptiness as by its brilliant threads. While the great walls and filaments represent the crowded cities of the universe, the spaces between them are the ultimate cosmic deserts known as voids. These are the true backwaters of existence, regions of staggering emptiness that stretch for hundreds of millions of light years. If a great wall is a sprawling metropolis, a void is the vast, silent ocean you must cross to reach the next one. Within these voids, the density of galaxies plummets to almost nothing. Where a supercluster might contain tens of thousands of galaxies, a void of similar size might host only a few dozen lonely, isolated island universes, adrift in an immense and terrifying darkness. These are not small pockets of nothing. The Boötes Void, one of the first and most famous discovered, is a spherical chasm of space roughly 330 million light-years across. To cross this single empty region, light would need to travel for over 300 million years. If our Milky Way were placed at its center, we would not have known other galaxies existed until the mid-1960s, when our telescopes finally pierced the edge of this colossal nothingness. The existence of these voids is not a cosmic accident. They are a fundamental part of the universe's structure, the negative space that gives the cosmic web its form. In the early universe, tiny quantum fluctuations were stretched to immense proportions by a period of rapid inflation. Slightly denser patches became the seeds for galaxies and filaments, while the underdense regions evolved into these vast, expanding bubbles of near emptiness. The gravitational tug-of-war shaped everything. Matter flowed out of the voids and into the filaments, draining these deserts and further enriching the already dense walls. So, to truly comprehend the scale of the largest structures, you must also appreciate the scale of the emptiness they border. The Hercules-Corona Borealis Great Wall is not just 10 billion light-years of something, it is 10 billion light-years defined by an even greater expanse of nothing. This grand cosmic architecture, a delicate balance between the immensely full and the profoundly empty, leads us to a final, unsettling frontier, a place where the very concept of a structure may reach its absolute limit. Yet even these webs and voids are not the final word on cosmic size. There exists another category of colossal entity, a single, unified object of almost unimaginable scale, the supergiant elliptical galaxy. These are not the graceful, spinning spirals like our Milky Way, but the ancient, bloated titans that sit like monstrous spiders at the very centers of galaxy clusters. The most famous of these is IC 1101, a galaxy so immense it defies easy comparison. If our solar system were the size of a penny, the Milky Way would be about as wide as the continental United States. On that same scale, IC 1101 would be larger than the entire Earth. Its true physical diameter is staggering, estimated to be up to 4 million light-years across. That means a signal traveling at light speed would need 4 million years just to go from one edge of this single galaxy to the other. This single object is wider than the entire distance between our Milky Way and its great rival, the Andromeda Galaxy. Its population of stars is just as mind-boggling. Where our galaxy holds a few 100 billion stars, IC 1101 is thought to contain 100 trillion suns, a number so large it eclipses all the grains of sand on every beach on Earth. This is not a galaxy in the sense of a tranquil island universe. It is the final, accumulated core of an entire galactic empire, the product of billions of years of violent mergers where entire galaxies have been consumed and assimilated. It is the ultimate cosmic cannibal, grown fat at the heart of its cluster, and it stands as a stark reminder that sometimes the biggest things are not the structures that bind, but the singular, monstrous objects that reside within them. But the universe is not defined only by the voids and the structures that span them. There is another kind of behemoth, a single, brilliant point of power that can dwarf entire solar systems on its own. We have been exploring the architecture that binds galaxies together, but now we must shrink our focus to the individual titans that light them up. These are the hypergiants and red supergiants, the largest known stars in the cosmos. To understand their scale, we must first shrink our own sun down to a single pixel on a vast screen. That tiny point of light, which contains 99.8% of all the mass in our solar system, becomes a mere speck. Now let that pixel grow. It swells first to the size of a marble, then a beach ball, then it consumes the entire screen and keeps expanding. This is the scale of a star like UY Scuti. If you were to place this star at the very center of our solar system, where our sun is now, its searing, tenuous outer atmosphere would not stop at the orbit of Earth. It would not stop at Mars. It would reach all the way out, engulfing the gas giant Jupiter and its family of moons in a sphere of incandescent plasma. The entire inner solar system, out past the asteroid belt, would be inside this star. Another contender, Stephenson 218, is so voluminous you could fit over 10 billion of our suns inside its gaseous envelope. These are not just large stars, they are cosmic balloons of almost impossible proportions, so vast and unstable that they pulse and shudder, shedding their own mass into space in violent eruptions. They are the ultimate examples of stellar grandeur, proving that sometimes the most immense things are not the structures that contain the light, but the luminous engines themselves, burning with a ferocious but fleeting intensity. Yet the most terrifying giants are not the largest in physical size, but those that wield the most concentrated power. Deep in the cosmic past, astronomers observe objects that outshine entire galaxies from a region no larger than our solar system. These are quasars, the active hearts of distant galaxies, and they represent a different kind of bigness entirely, one of pure, unadulterated energy. A quasar is not the galaxy itself, but its incredibly bright, hyperactive nucleus. The engine behind this brilliance is a supermassive black hole, a gravitational monster with a mass equivalent to billions of suns. The black hole's event horizon, the point of no return, is relatively tiny, but its influence is catastrophic. As vast clouds of gas, dust, and even entire stars are pulled into its grip, they do not simply vanish. Instead, this material is whipped into a frenzied, flattened whirlpool known as an accretion disk. Friction within this disk heats the material to millions of degrees, causing it to glow with the intensity of 1 trillion stars before it is finally swallowed by the darkness. The energy released in this final, violent feast is so immense that the quasar's core can outshine every single star in its host galaxy combined. Think of a single, brilliant lighthouse beacon so powerful it makes the entire coastline of a continent seem dim. That is the terrifying scale of a quasar's luminosity. It is a cosmic paradox where a point of ultimate darkness becomes the source of the most blinding light in the universe, proving that the biggest presence is not always about physical volume, but about the sheer, raw force it commands. These points of ultimate darkness are also the universe's true heavyweights. While quasars reveal their power through blinding light, the silent, dormant supermassive black holes that lurk at the heart of nearly every large galaxy command awe through sheer, incomprehensible mass. Our own Milky Way has one, a relatively quiet giant known as Sagittarius, a star. With a mass of about 4 million suns, it is a sleeping monster whose gravity dictates the orbits of stars whipping around it at thousands of kilometers per second. Yet this is just a modest example. In the galaxy Holmberg 15A, astronomers have found a true colossus, a supermassive black hole with a mass estimated at 40 billion times that of our Sun. 40 billion. To grasp that number, picture gathering every single star in the Milky Way and Andromeda galaxies combined, and then multiplying that number by about 10. That is the amount of pure mass crushed into a single point of infinite density. But how do you measure the size of something that, by its very nature, is a singularity, a point with no physical width? The answer lies not in the object itself, but in the boundary that defines its absolute power, the event horizon. This is the point of no return, the invisible spherical surface surrounding the black hole where the escape velocity equals the speed of light. Cross this line, and not even light itself can fight its way back out. The size of this sphere is defined by the Schwarzschild radius, a concept that directly links mass to gravitational dominance. For our Sun, its Schwarzschild radius would be a mere 3 kilometers. For the Titan in Holmberg 15A, that radius stretches to an astonishing 1,200 astronomical units. That means if you could place this black hole at the center of our solar system, its event horizon, the point where reality ends, would extend far beyond the orbits of all the planets, swallowing the inner solar system and the Kuiper belt, reaching a quarter of the way to the next star. This is the paradox of a black hole size, a physical presence defined not by solid matter, but by the warping of space itself into a gravitational prison from which there is no escape. To witness the birth of a cosmic continent, we must look back billions of years. Deep within the early universe, long before our Sun was even a spark, the first seeds of the largest structures were already taking root. These are the galaxy protoclusters, the primordial clouds from which the future giants of the cosmos would emerge. They are not the brilliant, defined cities of galaxies we see today, but vast, chaotic nurseries of creation, sprawling across hundreds of millions of light years. Picture a colossal, swirling fog of primordial hydrogen and helium gas, a cloud so immense it contains the raw material for millions of future galaxies. Within this churning nebula, the very first stars are igniting, and small, infant galaxies are beginning to clump together, drawn by the irresistible pull of their shared gravity. This entire teeming region is in a state of violent collapse, slowly condensing and heating up as it funnels into the gravitational well that will one day become the heart of a galaxy cluster. We are seeing the future Virgo supercluster, or even Laniakea, in its earliest, most embryonic form. It is the biggest single thing in the universe, not as a finished structure, but as a single, coherent event of becoming, a continent caught in the act of pulling itself together from the formless void. Observing these protoclusters is like looking at the blueprint for a cathedral while the foundation is still being poured. The final shape is not yet visible, but the immense scale of the ambition is already clear, a promise written in gravity and gas that will take billions of years to fulfill. The true giants of the cosmos are completely invisible to our eyes. All those brilliant galaxies and staggering walls are merely the glittering light strung upon a far more massive, unseen framework. This hidden giant is dark matter, a substance that does not emit, absorb, or reflect any light, yet its gravitational influence is the only thing powerful enough to sculpt the universe on its grandest scales. Every single galaxy, including our Milky Way, is embedded within a vast spherical halo of this mysterious material. This halo is not a small cloak. It is a colossal, diffuse cloud that extends far beyond the galaxy's visible edge, containing up to 10 times more mass than all the stars, gas, and dust combined. Picture a city of light floating at the heart of a ghostly, planet-sized atmosphere you can neither see nor touch. An atmosphere whose gravity alone keeps the city from flying apart. This is the relationship between a galaxy and its dark matter halo. Without this invisible anchor, the rapid spin of a spiral galaxy would fling its stars into the intergalactic void. The true size of a galaxy, therefore, is not the span of its stars, but the immense reach of its dark gravitational field, a sphere of influence that can span millions of light years. When galaxies gather into clusters and superclusters, their individual dark matter halos merge and overlap, weaving together to form the cosmic web itself. The great walls and filaments are not just chains of galaxies, they are the densest intersections of this dark cosmic skeleton, the places where the invisible rivers of gravity flow deepest. What we see with our telescopes is just the decorative icing, while the dark matter provides the massive, hidden cake beneath. This means the single biggest connected entity we know of, the Hercules-Corona Borealis Great Wall, is fundamentally a structure of dark matter, a single, titanic knot in the universal fabric that just happens to have galaxies tracing its outline. So when we ask what the biggest thing in the universe is, the most profound answer may not be a thing we can see at all, but the invisible, gravitational glue that holds the entire visible cosmos together. But what if the ultimate answer has been surrounding us all along? Could the single biggest thing simply be the entire observable universe itself? This is the final and perhaps most profound candidate for our title. The observable universe is not the entire cosmos, but rather our own limited view of it, a spherical region of space from which light has had time to travel to our telescopes since the moment of the Big Bang. Its boundary is not a physical wall, but a horizon in time, a limit to how far we can possibly see. The light from galaxies at this cosmic horizon has been journeying for nearly 13.8 billion years to reach us, showing us the universe in its ancient infant state. Yet, due to the relentless expansion of space itself during that immense journey, the current physical distance to the edge of our observable sphere is a staggering 93 billion light-years across. This single fact is almost a magic trick of cosmology. The universe is not 93 billion years old, but the space within it has stretched so much that the region we can observe is far wider than the age of the universe would naively suggest. We are at the center of this colossal sphere, not because we are special, but because every observer in the universe sits at the center of their own observable horizon. Yet, this magnificent sphere, containing everything from the nearest star to the most distant quasar, from the Hercules-Corona Borealis Great Wall to the vast cosmic voids, is almost certainly not the whole story. Most cosmologists believe the universe beyond our cosmic horizon is vastly larger and could even be infinite, filled with more galaxies, more walls, and more emptiness stretching forever into the darkness. The observable universe is the biggest single thing we can ever hope to measure or know, a self-contained cosmic island defined by the finite speed of light and the relentless flow of time. Our cosmic horizon is not the end of reality, only the limit of our sight. Beyond that boundary of ancient light, the true nature of existence may be far grander and more bizarre than we can fathom. This is where we confront the ultimate speculation, the concept of the multiverse. In this radical picture, our entire observable universe, with its 93 billion light-year span and all its great walls, is merely a single bubble in a frothing, possibly infinite cosmic ocean. The very idea of the biggest thing is shattered and reborn on an unimaginable scale. One compelling theory arises from the concept of eternal inflation. It suggests that the rapid expansion of space that began our universe never truly stopped everywhere. Instead, our entire cosmos is just one region where this inflationary energy decayed, allowing for stars and galaxies to form. Beyond our bubble, the inflationary vacuum continues to stretch at an incomprehensible rate, constantly giving birth to new, disconnected universe bubbles with potentially different fundamental laws of physics. In this eternal foam, the concept of biggest becomes meaningless, as the metastructure containing all bubbles is likely infinite and unending. A completely different path to the multiverse comes from the quantum realm, known as the many worlds interpretation. Here, every single quantum decision, every random event, does not just settle on one outcome. Instead, reality continuously splits, branching into a near-infinite tapestry of parallel universes where every possible alternative actually happens. In one branch, you might be listening to this very sentence, while in another, an entirely different version of reality unfolds. This is not a structure in space, but a fractal tree of possibilities growing with every moment. So, is the multiverse the final answer to our question? It pushes the idea of biggest to its absolute theoretical limit, suggesting that everything we have explored is a minuscule fragment of a greater whole whose full extent we may never and can never measure. The search for the biggest thing ultimately leads us to the edge of knowledge itself, staring into a sea of infinite potential. This immense gravitational pull we feel across the cosmic continent all flows toward a single, mysterious destination. The Great Attractor acts like a hidden vortex in space, a point of such profound gravity that it commands the motion of our entire local universe, pulling millions of galaxies, including our own Milky Way, on a slow, relentless journey. We are not drifting aimlessly, we are falling. For decades, this attractor was a profound cosmic puzzle because it lies in an obscured region of the sky, hidden behind the dense stars and dust of our own galaxy's central plane, a zone of avoidance that blocked our view. Its presence was not revealed by a brilliant beacon of light, but inferred from the silent, unified motion of countless galaxies all streaming in the same direction, like iron filings drawn to a colossal, unseen magnet. The force required to orchestrate this grand cosmic migration is staggering, suggesting a concentration of mass equivalent to tens of thousands of Milky Way galaxies all packed into a relatively small region of space. This defines a different kind of bigness, one not measured in light years of width, but in the sheer, overpowering command of gravitational force. It is a giant whose presence is felt not by the light it emits, but by the irresistible tide it creates in the fabric of space-time, a current that sweeps entire galactic clusters along for the ride. The true identity of this behemoth is now believed to be the dense core of the Laniakea Supercluster, a monumental knot where the cosmic web's filaments converge, piling an unimaginable amount of both visible matter and dark matter into a gravitational well of epic proportions. Our home galaxy and everything we know is caught in its flow, reminding us that the biggest things are not always the most visible, but are often the forces that silently shape our cosmic destiny. The Boötes void is a perfect case study in cosmic emptiness. Its discovery was not the result of spotting a dark patch, but a meticulous survey of galaxy positions in the 1980s. Astronomers were mapping the heavens when they stumbled upon a spherical region of space, a colossal bubble in the cosmic web that was almost completely barren. The scale they measured was staggering. This void spans approximately 250 million light-years across. To cross this single empty expanse, a beam of light would need to travel for 250 million years. If our Milky Way were placed at its center, the night sky would be almost pitch black, with the nearest major galaxies lying far beyond the edge of this nothingness. The emptiness is not quite absolute, however. Against all odds, a few dozen galaxies have been found adrift in this vast desert. These are not vibrant spirals like our own, but often isolated, lonely islands of stars. Finding them is like discovering a single, tiny hut in the middle of the Sahara, with thousands of miles of empty dunes in every direction. Their very existence is a puzzle, challenging our understanding of how matter clumped together after the Big Bang. This void is not a flaw in the universe, but a fundamental feature. It is the ultimate negative space, a volume so immense that its defining characteristic is what is missing. The Boötes void proves that emptiness itself can be a structure of almost unimaginable scale, a breathtaking monument to the profound nothing that balances the brilliant something of the cosmic web. But our journey does not end with the map of what we can see. Beyond the observable horizon of galaxies and dark matter lies the realm of pure theory, where the fabric of reality itself might be knotted into structures of such immense scale they make the Hercules-Corona Borealis Great Wall seem quaint. These are the theoretical giants, cosmic strings, and domain walls, hypothetical defects forged in the unimaginable heat of the universe's first moments. Picture the early cosmos not as a smooth, expanding fireball, but as a bubbling cauldron of fundamental forces undergoing a series of dramatic phase transitions, much like water freezing into ice. As the universe cooled and expanded, these forces settled into their current state, but the transition may not have been perfectly smooth. In some theoretical models, cracks and wrinkles could have formed in the very structure of spacetime. A cosmic string is envisioned as one such crack, an infinitely long, one-dimensional flaw in reality, thinner than a single atom yet possessing unimaginable density. A single inch of this cosmic thread could weigh more than an entire mountain range. These are not strings you could ever cut or touch. They are scars in the geometry of the cosmos, and their gravitational influence would be so profound that they could warp the light from distant galaxies, creating double images and acting as gravitational lenses across the sky. Even more staggering is the concept of a domain wall. Imagine a two-dimensional sheet, a membrane of pure energy separating entire regions of space where the fundamental laws of physics are different. These walls would not be solid in any normal sense, but rather boundaries between different vacuum states of the universe. A single domain wall could stretch across billions of light-years, a true partition in the cosmos. While no conclusive evidence for these structures has ever been found, their potential existence stretches our imagination of what is possible, suggesting that the true architecture of everything might be woven from flaws and boundaries on a scale that truly defies comprehension. This grand quest for the biggest thing confronts a fundamental obstacle, the challenge of measuring the unmeasurable. Our most powerful telescopes, like Hubble and its successor, the James Webb Space Telescope, are incredible time machines peering back to the dawn of galaxies. Yet they have their limits. They can only collect the photons that actually reach them, and the further we look, the fainter and more stretched those signals become. This stretching is known as redshift, a direct consequence of the universe's expansion. As space itself stretches during the light's multi-billion-year journey, the light waves are pulled longer, shifting toward the red end of the spectrum. This tells us the universe is expanding, but it also distorts our measurements of distance and size, forcing astronomers to become cosmic detectives working with clues that have been subtly altered by the journey itself. We are not just looking across space, we are looking back through an expanding and evolving cosmos, trying to pin down the true dimensions of phantoms from the deep past. But even if we could measure with perfect precision, a deeper philosophical problem remains. Where does one structure end and another begin? The cosmic web is a continuous, interconnected network. Is the Hercules-Corona Borealis Great Wall truly a single object, or is it just a particularly dense knot in the universal tapestry, a temporary confluence of filaments that we have arbitrarily given a name? When everything is connected by gravity and the fabric of space-time, the very idea of a separate, distinct entity begins to blur. Our search for the biggest thing is not like finding the largest mountain on Earth, a solitary peak against the sky. It is more like trying to determine the largest wave in an entire ocean, a transient feature in a fluid, dynamic system. This is why the search is never truly over. Each new survey, each more powerful telescope, refines our map and challenges our definitions, reminding us that the universe is not just a collection of objects, but a single, evolving story whose grandest chapters we are only beginning to read. So where does this leave our search for a single champion? We have journeyed past stars and galaxies, through superclusters and voids, to confront several ultimate titans, each claiming the crown in a different way. The Hercules-Corona Borealis Great Wall stands as the largest known structure, a filamentary behemoth spanning 10 billion light-years, a connected arrangement of galaxies and dark matter so vast it seems to challenge the cosmological principle itself. Then we have the supermassive black holes, the uncontested champions of concentrated mass. A single one of these gravitational monsters can hold the equivalent of 40 billion suns within an event horizon that could engulf our entire solar system, a point of infinite density commanding unimaginable gravity. And finally, there is the observable universe, the ultimate defined region. This is the entire sphere of space from which light has had time to reach us, a cosmic island 93 billion light-years wide containing every star, every galaxy, and every great wall we could ever hope to see. Placing these three contenders side by side reveals the true nature of our quest. The Hercules Wall is a component within the observable universe, while the black hole is a speck of immense density within the wall. There is no single answer, only a hierarchy of scale that depends entirely on your definition of biggest. Are you measuring physical width, concentrated mass, or the total volume of a knowable region? Each of these cosmic giants represents a different extreme, a different way for the universe to express its grandeur. This layered reality is perhaps the most profound discovery of all, revealing a cosmos built on multiple, simultaneous levels of immensity. Our journey began in the familiar confines of our own solar system, a realm that already stretched the limits of human imagination. We then sailed across the galactic ocean of the Milky Way, joined the local cluster of galaxies, and found our place within the immense continent of Laniakea. We pushed further to the billion light-year walls and the silent, terrifying voids that separate them, finally confronting a structure so large it seems to defy the universe's own rules. We have met stellar titans whose hearts could swallow our sun, and black holes whose gravitational shadows are larger than our entire solar system. And through it all, we have seen that the invisible hand of dark matter sculpts everything on this grandest of stages. The answer to our initial question, what is the biggest thing, was never a single name. It is a spectrum of giants, each a champion in its own right. The crown shifts depending on whether we measure by physical width, by sheer concentrated mass, or by the total volume of a knowable realm. This layered reality, this hierarchy of scale, is the true wonder. It reveals a cosmos that is not just vast, but complex and beautifully structured on every level we can perceive. So the next time you find yourself under a clear, dark sky, remember this. Every single pinpoint of light you see is not just a star, but a potential sun. Every faint, fuzzy smudge is not just a cloud, but an entire galaxy of billions of suns. And you are standing on a pale blue dot, looking out at a cosmic tapestry whose full grandeur we are only beginning to understand. That sense of awe you feel is the most honest response to a universe that continually redefines what is possible.